We've spent 2 videos in the sun. Now we turn to the wind. And we start with a question you've probably never stopped to ask: why is a wind turbine blade shaped the way it is? Look closely and a blade is strange. It's twisted along its length. It's wide at the root and narrow at the tip. And almost every large turbine has exactly 3 of them. None of that is by accident. Every one of those features falls out of a single piece of engineering, the theory that tells us how much power a blade pulls from the wind, and what shape pulls the most. It's called blade element momentum theory. We'll build it from 2 simpler ideas, momentum theory and blade element theory. Watch them locked together into a system Python can solve by iteration, and finish by computing the power a real rotor captures. Let's get into it. Forget the blades for a moment. Picture the spinning rotor as a simple disk that the wind blows through. As the disk pulls energy out, the air behind it has to slow down. Far upstream, the wind moves at its full speed. By the time it reaches the disk, it's already slowed, and downstream it's slower still. The flow widens to carry the same mass of air. We measure that slowdown with a single number, the axial induction factor, A. At the disk, the wind has dropped to 1-a times its original speed. It's the first of the unknowns we'll solve for. And momentum theory gives us something remarkable: a hard ceiling. No turbine, however perfect, can capture more than 59.3% of the wind's energy. That's the Betz limit, and every real design is measured against it. Now we bring the blade back, but we only look at one thin slice of it. Up close, that slice is just an airfoil, a wing, sitting in a flow of air. 2 winds hit this slice. The first is the slowed oncoming wind we just described. The second comes from the blade's own rotation, sweeping through the air. The rotation also nudges the air around, and that's our second unknown, a prime. Add those 2 together and you get the relative wind, W, the airflow the slice actually feels. The angle it makes with the rotor plane is the inflow angle, phi, our third and final unknown. Here's the key insight. The rotational speed grows the further out you go along the blade. So the relative wind arrives at a different angle at every radius. To keep each slice biting the wind at its best angle, the blade has to twist and taper from root to tip. That's why it's shaped the way it is. Here's the trick that ties it together. Momentum theory and blade element theory describe the very same forces on the disk, from 2 different directions. So they have to agree. Set them equal and you get 3 equations and 3 unknowns: the axial induction A, the tangential induction A prime, and the inflow angle phi. The catch: they're tangled together. You can't just solve them in one step. So we do what Python does best: we iterate. Guess the inductions, compute the angles and forces, update the guess, and repeat. Each pass gets closer to the answer that satisfies both theories at once. And watch what happens when we run it. The numbers start from a rough guess and settle, in just a handful of passes, onto the values where everything balances. The axial induction homes in near a quarter, the inflow angle locks in around 8.5 degrees. That's convergence. We can now solve any slice of the blade. So we run the solver across every slice, add up the power each one captures, and get a single number for the whole rotor, its power coefficient, Cp. Now sweep the tip speed ratio, how fast the tips move compared with the wind, and plot Cp for each. A clear curve appears, and it never crosses the Betz ceiling, exactly as momentum theory promised. And there's the payoff. The power peaks at a tip speed ratio of about 8, pulling roughly 45% of the wind's energy. Run faster or slower than that, and you capture less. That single peak is why every turbine is tuned to spin at one particular ratio. So that's the whole chain. Momentum theory said the wind must slow down. Blade element theory looked at one slice and found the forces. Forcing them to agree gave 3 tangled unknowns, and a few lines of Python untangled them by iteration. And now you understand the blade's strange shape. The twist, the taper, the careful tip-speed ratio, none of it is decoration. It's all there to keep every slice of the blade biting the wind at just the right angle. The full solver is linked in the description. Point it at any rotor, any number of blades, any wind speed, and it'll tell you the power it captures. If this was useful, subscribe to Python for Engineers, where we keep turning the equations behind everyday engineering into code you can actually run. Thanks for watching.